So far, all the examples we've done have dealt with independent noise. But it's interesting to take independent noise and feed it into a process that will generate a correlated noise. So we can have a model of noise that is correlated, because there are many applications in which the random part of our system does not involve purely independent random process. Examples of this are time series or spatial patterns. There's going to be some correlations between near neighbors in the random part of the process. And so I want to do a simple example of this using what's called an autoregressive process. And this model is very simple, where the u of t are assumed to be normally distributed with variance sigma squared, and their IID is the jargon, which means independent and identically distributed. So the u's are independent, but the y's, which are related to the u's, are not going to be independent because of this beta 2 coefficient that relates the value of the y at time t to its value at y t minus 1. And this beta 2 will create correlations in y that are not present in u. And so we're going to first simulate some of these in MATLAB, and then we'll come back and look at what is the expected mean and variance of y, given that we know that the mean of u is 0 and its variance is sigma squared. So beta 1 is going to be the mean of y if beta 2 is 0, because the mean of u is 0, and if it wasn't for this beta 2 one, then we could see that the mean of y would just be beta 1. Here, beta 2 for the first time through, I'm just going to set it to be 0. So we can look at a time series of purely random variables, and then we'll change beta 2 and see what correlated noise looks like. And we say lag 1 because in this model, y of t is related to itself at lag 1. So that's the coefficient that multiplies y at t minus 1. If we had included a new coefficient beta 3 times y of t minus 2, then we would have what's called an AR2 process, autoregressive process of order 2. And you can imagine adding more and more previous time steps. So this will generate a t by 1 column vector of random variables whose mean is going to be 0 and whose variance will be sigma squared. And we're going to start off with the process. Since it's related to y at a previous time step, we're going to start it off at t equals 1, and for y of 0, we're going to assume that it starts at 0. Alright, so this is the generation of our AR1 process, and now we can make a plot. This is a realization of this process with beta 2 to be 0, so it's independent random variables, and the mean should be close to 1, which it looks like it is, and the variance should be close to 2, which looks about right. The square root of 2 is about 1.4, and that seems about correct. About 60%, 68% of the dots fall within plus or minus 1 standard deviation, or between 2.5 and minus 0.5. Now let's compare that to the case where I change this beta 2 coefficient. Make it 6. Now the swings are much bigger, and also the points don't seem to oscillate nearly as much. There seem to be some correlations in the sense that nearby values are kind of the same. The oscillations are more slow moving. Let's try it again. There's also this kind of transient part you can see at the at the beginning, it starts at 0 and it kind of drifts upwards towards the new mean value. Let's make it even bigger. So this is 0.9 for beta 2. And now you see this initial transient part where it climbs up and then it oscillates, but with these long time swings. Let me make it even longer so we can have a better look. So there's seems like a spin-up period that's pretty quick, and then it fluctuates with these fairly long swings back and forth. What if I make the coefficient even bigger? 0.99. And notice here that the limits are between -5 and 20. And now at 0.99 there's a very slow and gradual drift, and then there's these long excursion. Now what happens if I make it bigger than 1? Now things blow up exponentially. So it seems that beta 2 has to be less than 1 if we're not going to have explosive time series. And the special case for beta equal to exactly 1, beta 2 equal to exactly 1, that's known as a random walk. But that random walk with the drift, because beta 1, if I set beta 1 to be 0, I guess that would be a usual random walk. Let me put beta 1 to 0. Right, this is more like a typical random walk. Okay, so let's try to compute what the mean and the variance of y should be in terms of beta 1 and beta 2 and sigma squared. So I'll remind you that the expected value of f is the integral from -infinity to infinity. So that's the definition of these angle brackets, the expectation, and the mean of u. This expectation value is just 0 because the exponential, the Gaussian, is a symmetric function and u is anti-symmetric, so this integral is just 0. And then the variance of u, the expected value of u minus its mean squared. So that's the general definition of the variance in this case. Because the expected value of u is 0, this is just the expected value of u squared. Alright, so that was just to remind you. Now we're going to compute the expected value of y of t. So the expected value of beta 1 is just beta 1. The expected value of beta 2 times y t minus 1 is going to be beta 2 times the expected value of y t minus 1 plus the expected value of u of t. Now the expected value of u of t is just 0. So this is beta 1 plus beta 2. Now at this point, I can't make any progress on this. I know how the expected value of y at times t is related to the expected value of y at times t minus 1. A simple case is going to be where we have a process that's called stationary, and that means that these two are going to be equal to each other, and then I can just easily solve. So, and I'll explain what stationary means in a little bit. So if it's stationary, and we're just going to define that quantity to be equal to mu, and then I'm just going to substitute mu in this expression. So I have mu, and that allows us to solve for mu. And so the expected value of y is beta 1 divided by 1 minus beta 2. And this should point us to what we saw a while ago, that when we put beta 2 equals to 1, we had a random walk where things drifted off. And if beta 2 is made bigger than 1, then we found that the system would explode. But we don't see this from this expression. This seems like it would be perfectly fine to have beta 2 greater than 1. But that's not the case, because when we tried it, when beta 2 is greater than 1, we had explosive growth. So if beta 2 is greater than 1, the expected value of y at times t was certainly not equal to y of t minus 1. So it wasn't stationary when beta 2 is greater than 1. So this is provided beta 2 is less than 1. I think it's instructive to iterate this process by hand for a few steps, going backwards in time, so we can see if we can find the general formula. And now we're going to use the same formula, but with t set to t minus 1 to substitute in. And then simplify. And now we're going to use this formula to get ut minus 2 in terms of ut minus 3. And then the last terms. Let's simplify. And here I explicitly put beta 2 to the 0, which is this one, so we can see the pattern. Here, as if we keep iterating back, we'll have an infinite series of 1 plus beta 2 plus beta 2 squared plus beta 2 cubed and so on. So this will give us eventually, this term will go to beta 2 to the infinity, y at t minus infinity. So y, the initial condition set at minus infinity in the past, multiplying beta 2 to the infinite power. So this only makes sense if beta 2 is less than 1. Otherwise this will be infinity, so this won't make any sense. So we need the absolute value of beta 2 to be less than 1. But this is also the condition for this infinite series to converge. And then the last one with the random forcings is going to be the infinite sum from k equals 0 to infinity of beta 2 to the k times ut minus k. So when k is 0, we get this term. When k is 1, we get this term. When k is 2, we get this one. And if we get more and more terms if we keep iterating. This series converges if this is the case. So then if y of t is equal to beta 1 or 1 minus beta 2. That's the sum of this series, is 1 over 1 minus beta 2. This term vanishes, and then we have... So you see that the random perturbations from far back in time have decayed a lot by the time we get to time t, because they're raised to the power k. And this beta 2 is less than 1, so they damp out. Anyways, this is a good formula for us to calculate what the expected value of y of t and then its variance. So the expectation of this term is just going to be this term. This will be the infinite sum. Because the expectation is a linear operation, we can just take it inside the sum, and then all these are 0. So we just get beta 1 over 1 minus beta 2. And that's the same result we got a while ago for the case where it's stationary. Now for the variance, we take the expectation values of y of t minus mean squared. So the expectation is this quantity. If I subtract it from y, I just get this quantity, so we get the expectation of the infinite sum. Now it would seem that I would have to square an infinite series, but the beauty is that the u's are assumed to be independent from each other. So that means that is going to be 0 unless m is equal to 0. So we'll only come up with the squared terms. All the other terms will drop out. So all the cross terms will all vanish. Here, if I take the beta 2 to raise to the kth power outside of the expectation, we'll get a squared of this quantity. And these are all sigma squared, these expectations. And sigma squared is a constant when you pull it out of the summation. So we get sigma squared times the sum. And this infinite series is the same form as this one, except what used to be beta 2 is beta 2 squared. And so we found what the variance and the mean of y should be for our AR1 process. So let's go to the computer and check if these actually work out. All right, so we have a time series. We've set beta 1 and beta 2 to be 0 to get started. And now we're going to add dashed lines at plus and minus 1 standard deviation from the mean. And we'll also add a solid line where the mean is. So this is the mean plus 1 standard deviation, mean minus 1 standard deviation. Let's count the number of times it falls outside plus or minus 1 standard deviation. About 32%, which is about right. We should have about 68% within plus or minus 1 standard deviation. Now let's go and change our parameters. So let's pick beta 1 equals to 1, beta 2 equals to 0.4. That looks about right. Now the mean, 0 is here and the mean is up here, so the mean is not exactly 0. Let's increase it even more. And it still looks pretty good, and about 32%, more or less right. And so you have this brief period of spin up, but then you converge to the stationary state. Let's make it 0.99. So you can see these very long swings up and down, because now the memory of the system is quite good. It remembers its past, because the decay over here, this decay is very slow. And so perturbations from the past take a long time to damp out. Okay, so that's the AR1 process. A useful diagnostic for time series processes is the autocorrelation function, which measures how correlated 2 points in a time series are based on how separated they are in time. First, we define the autocovariance function. And then we use the autocovariance function to define the autocorrelation function, which is just the autocovariance function normalized by the lag 0 autocovariance. So as a particular example, let's look at the time series, the AR1 process we've been looking at. And we found so from this, we can evaluate the autocovariance function for this process. And of all the cross terms, the expected value of them will all vanish unless t minus I is equal to t minus k minus j, because all the other u's are independent. So unless these are the same noise, then their expected value will be, the expected value of their products will be 0. So we have to find t minus I equal to t minus k minus j, which means that I is going to be equal to j plus k. This infinite series just sums to 1 over 1 minus beta 2 squared. And so the autocorrelation function will be, because the lag 0 is just sigma squared over 1 minus beta 2 squared. Let's try it out in MATLAB and see if this works out. Let's start off with the pure noise time series. And now we'll write our autocorrelation function. We have to make sure that our time series, we've subtracted the means from them. In gamma 1, we're going to put the lag 0 covariance. So we're going to compute it for 60 lags. And we're going to make a plot. I will also compute the theoretical value. Alright, so this time series is just random noise, no correlations. And if we look at the autocorrelation function, we have correlation of 1 at lag 0 as expected. And then after that, it just kind of bounces around very small values. Let's add in the plot of the theoretical value. Alright, and the theoretical value just goes to 0. So these are just due to the fact that we have a finite sample. That's why they're not exactly 0. Let's look at a case now where we have beta 2 different from 0. And now we can see that the autocorrelation doesn't drop to 0. There's kind of a smooth decay. If we make the time series longer, these ones over here that are just due to sampling variability are going to be much smaller. But if we do another realization, we'll see that these autocorrelations for lags greater than 10 or so are going to fluctuate quite a bit. And that's because our time series is only 400 units long, and so there aren't very many realizations of lags of 20 or more. But if I made the time series longer, then they're much smaller. And that's because now we have many realizations and we get a much more robust average of the autocorrelation at the longer lags. And this was for an autocorrelation coefficient of 9, and you can see there's a persistence almost all the way out to 60. Alright, that's the autocorrelation function for an AR1 process.